Hello everyone, this is Lee here. In this video we're going to do a review of the Kinematics unit. Now, just so you know, this is a review for where we are currently with our mathematical skills. So there are certain things that you will be expected to know by the end of the course, but I will not cover that yet in this review video. I will make another review video when we are actually at the end of the course, where we can do a nice little summary and see how kinematics ties into everything. Alright, let's begin. So to start off, the big idea behind kinematics is that it's the study of motion. So everything in this unit was something about how something moves. And from there, we had a couple of variables that we looked at and a couple of definitions. So let's start off with that. So we start off with the variable x, and this tells us our position. From there, we had different forms of it, such as XO and XF as initial and final position. We were also introduced to a new symbol, delta, which means final minus initial, or the change of. And so we said that delta x is another way of saying the change in position. Now that is just a very long way of saying displacement. Now, the equation for delta x is, of course, x final minus x initial is equal to delta x. And it really depends on what you have after the delta. It could be delta v or delta a, but whatever the delta is always a final minus initial form. Alright, so from there, we went over vocabulary terms, and we said that these two were vectors. Now, this is actually a very important thing. It might seem a very minor thing because we don't really solve problem solving for certain vectors, but the definition does come up a lot. And remind yourselves that vectors require both magnitude and direction. Okay, direction simply meaning up, down, left, right, positive or negative, and magnitude just means the number, how big something is or how small something is. So definitely commit this vocabulary term to memory. Okay, that's a star. All right. From there, we learned about distance, d. So d is the total, total distance traveled. I don't know, right? Distance traveled. And I think the important thing here is that this is a scalar. Okay, this is a scalar. So a easy comparison between distance and displacement is that they're kind of like the same thing, but distance is a scalar and displacement is a vector. Okay, so from that video, we went over just a very basic idea of what the biggest difference is between the two. I remember my example here is if we have two positions A and position B. Okay, if you travel up, let's say 3 meters, okay, and then you travel to the right, let's say 4 meters, your total distance would be 3 plus 4. So that gives us a total of 7 meters. Okay, but if we were to find the displacement, remember the displacement is the shortest distance between the 2 points. So this distance right there, we would have to use the Pythagorean theorem, a squared plus b squared equals c squared, and in this case, the c squared would be 5 meters. So your displacement would be 5 meters. Oftentimes, not always, but the displacement is usually shorter than the distance, as you can see here. Okay, yeah, and in this case, because displacement is a vector, we can say northeast, or up and to the right, whatever the case is. Or we could find this angle and just tell us what the angle is. That will give us our direction. Okay, so from there, we went into the definitions of speed and velocity. All right, so speed is your total distance divided by the time, and speed is a scalar. So it just cares about the number. Another way to memorize this, or how I memorized it back in school, was that speed starts with an S, and so does scalar. Okay, so a example of speed could be like 4 meters per second. Velocity is the change in position, aka the displacement over the change in the time. And a velocity is, of course, a vector. And once again, how I memorized it back in school was that velocity starts with a V, and so does vector. Now I gotta start using the proper notation. If it's a vector, there's a tiny little arrow on top of it to designate that it's a vector. Okay, an example of this could be 4 meters per second north, 4 meters per second positive, right, or negative 4 meters per second south. Okay, so those are all examples of velocities. Okay, now I do have to make an important note. Whenever you use this form of the equation, we'll hardly ever use speed, but we will be using velocity a lot. Okay, when you're using this form of velocity, you can only use if your acceleration is 0 meters per second squared. Okay, you can only use this form of the equation if you have a constant velocity. So I should write that down. This is a constant velocity equation. It is not instantaneous velocity. Okay, it is just a constant average velocity, and you can only use that if the acceleration is 0. Now this is this right here is very important. I'm going to highlight that because that is the fundamental idea behind what we're going to cover next, and that is the kinematics equations. Okay, so I'm going to write the 3 kinematic equations up on the screen. On the AP Mechanics equation sheet, they do come off as a little bit different. I think I'll try to write it exactly the way that it's written on the equation sheet. So we have x final is equal to initial position plus vxo times time v times t plus 1/2 a sub x t squared. Now just so you know, these tiny little subscript x is just telling you that it could be in a x, y, or z direction. Okay, that's what those tiny little subscripts mean. So this is the first equation, followed by v is equal to v initial x plus a sub x t. Okay, once again, those tiny little subscript x's just tell us that it could be in a x, y, or z axis. And the final one is v squared is equal to v initial x squared plus 2 a sub x final position minus your initial position. Okay, so here are our 3 kinematics equations. Now, the reason why we have these 3, and this is what's important, this is one of those highlighter kind of moments, we can only use if there is constant acceleration. Okay, and we notice, because notice in all 3 of these equations we have the variable a, versus up here with the delta x over delta t, there is no acceleration a, okay, because the acceleration is 0. So we can only use, well, we can use these 3 equations for any problem, even if the acceleration is 0. If the acceleration is 0, like mathematically, you'll end up with the equation that we discussed up here. But just so you know, that these 3 equations are used because we have a acceleration. All right, so that's one of those highlighting kind of moments. That's a big idea behind these 3. All right, from there, we learned about instantaneous velocity. Okay, so I'm not going to go behind the theory and behind the idea of instantaneous velocity, but I will go over what you need to know in order to find instantaneous velocity. So if you're given a function, let's say x of t is equal to, I don't know, 2x squared minus 3x, in order to find the velocity function, you have to take the derivative. Okay, so derivative to find vt. So we can write it as dx dt. And once again, I know we're not used to this notation right here, but this is the notation that I am the most comfortable with for this course because of the way that we can work around the mathematics. So try to get in the habit of writing in this fashion. Right? So the derivative of that, we did the power rule, so 4x minus 3 will give the function for velocity. And so I can write this as v sub t. I keep on getting in the habit of writing x's where I should write t's. Excuse me. So this should be 2t squared minus 3t. There we go. All right. So the idea is if you're given a, so if I were to summarize, if given a position function, take derivative to find a velocity function. Okay? All right. Now, once you have the velocity function, you can plug in different numbers, okay, to solve for whatever the problem is asking you to solve for. And at this point, we were introduced to a very important keyword, and the idea is called rest. Okay, so if the word problem says that the object is at rest, you should know that your v sub t, whatever it is equal to 0. Okay, 0 meters per second, and that is the object that is at rest. All right, So from there, we took it to the next level. We combine our knowledge of acceleration, and before we do that, let's define acceleration. So A, aka acceleration, right? Acceleration is the change in velocity over the change in time. Okay, that is the equation for average acceleration, change in velocity over change in time. And simply put, acceleration does not tell you how fast something is moving, but it does describe the motion. Okay, the acceleration tells you if it's speeding up, if it's slowing down, or if it's changing direction. And once again, we didn't do changing direction, but we will. But the first two are definitely the ones that we worked on for this unit, speeding up or slowing down. Now here's an important idea here. All right. In one of my videos, I asked you to copy down the velocity acceleration chart, and I'm going to do a brief version of that chart. So we have a velocity, acceleration, and a speed up, slow down chart, right? And so we stated that if the velocity and the acceleration, okay, if they are the same, then the object is speeding up. We also stated that if the velocity and the acceleration are opposites of each other, they are slowing down. We also stated that if your velocity is 0, but if you have a acceleration that's either positive or negative, the object will speed up in the accelerating direction. Now, just so you know, if your velocity is 0, there is no motion, okay, for a brief moment, but then it starts to move, all right? But it starts to move. So I'll write that in. Now, the reason why this is important, because when you come up with a number, let's say you're given a word problem scenario, and you accidentally say, like, let's say the velocity is negative, but it should be positive, and like you read through the problem, and you're like, okay, the object is supposed to be slowing down, my acceleration is negative, and my velocity is also negative. Doesn't that mean it's speeding up, right? So chances are you either made a calculator mistake, or you accidentally put a negative in there when you shouldn't have. Okay, so that actually does come up a lot. So this chart is very important to keep in mind as you're answering the problems. When you're asking yourself, does this answer make sense? Okay, in the context of the problem as a whole, does it make sense? All right. So we learned about acceleration as a change in direction, and with this idea of, with a change in velocity. And with that idea of change in velocity, we said in order to get from a velocity function to a acceleration function, we have to take the derivative. And as a good review, I'm going to take the derivative of what we have up here. Okay, we said it was 4t minus 3. And so if we take the derivative of that, we will end up with 4 meters per second squared. Okay, the 3 cancels out. All right. So in order to find the acceleration function, you would just have to take the derivative. All right. Now, the reasoning behind taking derivatives. You won't have a question directly that asks you, why do we take derivatives? But the idea behind the reason why we take derivatives is important. Okay. So once again, in that video, I went over in very big detail what a derivative means. But what you need to know is that a derivative, you are measuring tiny changes. Okay, tiny changes. And this is important with the idea because we know that a change in position over time, okay, this gives us velocity. So in order to find the velocity function, we take the derivative of a position function. Okay, and we also learned that if we have a change in velocity over a change in time, we are finding the acceleration. So what this means is we are finding the changes in the velocity function to find acceleration. Okay, so the definition of what's good for us in terms of derivatives, like it's a very simple definition, but the definition works. Finding the tiny little changes is what a derivative is. And if you find the change in a function, it often leads you to understand what you're looking for. Okay, so we did that. And next we went into the kinematics stuff, right? We actually used the kinematics motion or equations, and we went into projectiles. So I want to do a very, very brief idea of the projectile motion unit. Okay, once again, if you need more review, check out that previous video. But I just want to do the highlights, right? The greatest hits of the projectile motion unit. So we have a surface, all right, and if we have a projectile, and the projectile is launched and it lands, let's say, at the same level. All right. Now it won't always be like this. Sometimes you'll land on a building. I'll erase this one, but sometimes, let's say there's a building like that. Sometimes you might land on that building. Okay, but I'm just doing it for if it lands on the floor. All right. So a couple of key things. Usually your initial position is going to be 0 unless given to you, and your final position is something that you usually have to find. All right. The final position is always called the range. All right. At the highest mark, the peak. Okay, so I'm going to label this the peak. A couple important things there is that your velocity in the y direction is 0. It is neither going up nor down. It is just moving forward. Okay, so your velocity of y is 0. However, your vx doesn't change, right? Your vx is still your v initial x. So that's a important idea here. Your v initial x is equal to v final x because, okay, the reasoning is important. So your velocities don't change because your a sub x is 0. There is no change in the x direction. So that's a highlighting one right there. Very important. All right. The important thing to know that as you rise up, okay, your velocity y decreases. Okay, and I represented that using my vectors. In the beginning, I have a big y velocity vector, but towards the peak, my velocity y vector bit gets smaller. It gets so small until it doesn't exist anymore. And after a couple of time that passes, your velocity y decreases. Okay, as in it just goes into the opposite. Excuse me, I shouldn't say decreases. It turns negative. Okay, it turns negative, but it's increasing in the negative direction. All right, so comparing that to here versus to here, right? The y velocity is constantly increasing. Now, what is that increasing rate? So it is here when it's falling, it increases at a is equal to negative 10 meters per second squared. Okay, and up here, your y velocities, vy changes by decreasing at a rate of negative 10 meters per second squared. Okay? And the important idea here is when you're rising up, your velocity is positive, but your acceleration is negative. Therefore, we are slowing down. Once again, that chart is rearing its head again. And over here, while we're falling, your velocity is negative, your acceleration is negative. Therefore, we are speeding up. Okay? All right. A couple of other important things to know is whenever you're given a velocity vector, we can break apart that vector into its x and y components. So usually you're given v initial, and so you can find v initial y and v initial x, right? And never don't memorize like v initial y will always be sine, v initial x will always be cosine. Please don't memorize it like that. Always use the method of actually figuring it out, solving it through, right? Locate the angle and see on the opposite side. Okay, so that's the opposite side. Therefore, this is sine, and v initial x. Okay, that is adjacent. Okay, and therefore we will use the cosine function according to SOHCAHTOA. All right, and the very last thing is you can find the resultant vector. Okay, so you can find the resultant vector of anything by using the Pythagorean theorem. All right, so for example, if you have a sub x and you have a sub y, you can find the resultant a by using the Pythagorean theorem. All right, so if you have ay and ax, you can find a. All right, you can find v if you have vx and if you have vy by using the Pythagorean theorem. Right, so those are two vectors. Other vectors that we know, right? We know this is delta x, and we know that this is delta x, y, right? So displacement x and displacement y. So in order to find the resultant displacement, you can use the Pythagorean theorem to find the actual displacement. All right. So anytime you have a vector, okay, anytime you have a vector, you can find the resultant vector by using the Pythagorean theorem. All right, so the other thing that we can cover are the motion graphs. So I'm going to go over the different kinds of motion graphs. I will go over them in a little bit more extensive detail because it's good to see it over and over again. But the other thing about these motion graphs is we also covered the idea behind area under the curve and the slope. Okay, so let's do that right now. All right, so the first thing I'm going to do are all of my position versus time graphs. Okay, so here we have a position versus time graph, right? And so from here on out, I'm not going to label everything. They're all just going to be position versus time graphs. I'm going to do a position versus time graph like this. This is what we can say a constant velocity that is positive and your acceleration is 0. And we know that because this is a linear line. Okay, all right. So if I have another one, I'll do this one over here. Yeah, we'll go over. So if we have a position versus time graph, right, and we have something like this, we have a velocity that is 0. Excuse me, a velocity that is negative, which your acceleration is 0, and that's because the line is linear, okay, and therefore the velocity is not changing. Now the big idea behind these two is that your slope is your velocity, okay, for position versus time graph. All right, now let's do a object that is speeding up and a object that is slowing down. So if we have a position versus time graph, let's say we want to do a speeding up, okay, in the positive velocity direction. All right, so you can start anywhere. I'm just going to start down here. So we have a flatter curve at the beginning, and then we're going to curve up. Now the reason why I want this flatter curve, okay, there's a highlighted part right here. The reason we want a flatter curve is because this shows us that our velocity is 0 or close to 0, which just means that it is moving very slow. And as we curve up, that curving motion, the curve shows us acceleration. Okay, the examples before we had a straight line, no curves, right? But here we do have this curving motion, right? And then we end up with a positive slope. Therefore, we have a positive velocity. Now we know it's positive slope because one, the arrowhead is pointing up, but as I'm going from left to right, my pen went upwards. So here in this region, we have a positive velocity. All right, so if I were to do something similar, but let's say for a object that is slowing down in the positive, so we have a object that has slowed down and it had a positive velocity. Okay, so we want to start off with a positive velocity, and because it slows down, that means that the velocity over time will approach, so ZF will approach 0 meters per second. So it'll flatten out. So this part will be flat and this part will be vertical. All right, so we get something like this. And the reason why we know that it starts off with a positive velocity is because my line is going upwards, right? My line is going upwards, but then it kind of flattens out towards the end, which shows us that the velocity is approaching 0. Now on the other side, let's do a speeding up. So we can do a speeding up, but with a velocity that is negative. So if we are speeding up with a velocity that is negative, that means that we start off with a velocity that is pretty much 0, and then it gets more and more vertical, right? So we have something like this, right? And we can say that up here, where it's flat, right? The slope is flat, therefore your velocity is 0 or really close to 0. And down here, okay, this part is more vertical, so this is vertical, and therefore we have a great velocity. And in this case, the velocity will be negative because it's pointing downwards, right? So let's do a slowing down with a negative velocity. Slowing down with a negative velocity. So that means that we want to end up with a flat zone, but we start off with a steep negative velocity. So we're going to go down, okay, steep negative velocity, and then we, boom, flatten out. Right, so this is slowing down with a negative velocity. Right. So those are the 4 different kinds of graphs that you are expected to know. Next, we'll do a velocity versus time graph. All right. So velocity versus time, in my opinion, it's a little bit easier. Because I think the hardest part about these graphs is, one, you just gotta look at what the axes, what the variables tell you. So I'm going to do the constant velocity. All right, so we have constant positive velocity and your acceleration is 0. Okay, no change. Boom. Let's do a constant negative velocity where your acceleration is 0. Boom, constant. Okay, this is positive because it's above the x-axis. This is negative because it's in the negative y region. All right. Notice here the accelerations are both 0, and we know that because the line is flat. So for a velocity time graph, the slope is your acceleration, and that's a very important one. Very important one. Your slope is your acceleration. All right. Now let's do a object that is. So we have velocity time. Let's do a object that starts from rest and it speeds up. Starts from rest, speeds up in the positive direction. V initial is 0. Okay, we know that from the starting point. And then your V final is positive. Okay, and it's sped up. Okay, so we know it speeds up. Therefore, acceleration has to also be positive. Right, same signs. And we notice because the slope, if you look at the slope, we have a positive slope. Now on the other side, if I were to do a object that is speeding up but in the negative direction, okay, remember negative does not mean slow. It would look like this. So your initial velocity would be 0 meters per second. Your V final would be negative. Your acceleration would also be negative. Okay, and we know this because it's speeding up. If the signs are the same, that means it speeds up. And we know that the acceleration is negative because your slope is negative. All right. So we get something like that, and from there, they like to kind of trick you up, and they'll give you a graph that looks like this. Okay. Now the important thing here is to look at the y-axis. All right. So I'm going to highlight at different parts. So let's call this part 1. Right there, part 1. So here we start off with a great big negative velocity. Okay. And here we have a slope. Okay, that is positive. So positive acceleration. So this must mean that it is slowing down. Positive slope, negative velocity, positive acceleration means that it's slowing down. And we know this to be especially true because right here, right, that's a very important part. Wherever you see a 0, very important. Your velocity is 0. So it pauses. So it's moving and then it's not moving. It came to a stop. Right? And then after that, we switch directions, right? So we have a positive velocity after that, and I'll highlight that part. Let's do a green. Boom, right there. So here we see that the velocity is positive, but your acceleration is also positive, and we know this because once again it is the slope. Therefore, we have positive, positive. The object is speeding up, and we know this especially be true because we start off with the velocity 0, and we ended up with a great big positive velocity. Right? Now the reverse is true. Okay, I won't go into it with too much detail, but if you're given something that looks like this. Okay, so here we have, I'll just point out the important parts. The slope is negative. Okay, therefore your acceleration is negative. Okay, up here we have a positive velocity region, so it's slowing down, and down here we have a negative velocity region, and the acceleration is still negative, therefore it is speeding up. Okay, so keep that in mind. And once again, the important part here is that 0 mark. It comes to stop. All right, so keep that in mind as you are reading these graphs. All right, final thing. Final thing. And this is, so we talked about slope, but we didn't talk about this other thing called the area under the curve. So if you're given a velocity time graph, okay, and let's say you're given a velocity time graph that looks something like this. This area that I'm going to color in, this area right here, so it's from the line to the horizontal axis. Okay, so this is the time, so this is the horizontal axis. You always create your area under the curve from the line to the horizontal axis. The area under the curve for a velocity time graph is your displacement. And the reason we know this is because area is equal to base times height. Or in this case, our base was our time axis, and our height will be our velocity. So velocity times time gives us our displacement. Okay, and we discussed that at the very beginning of the review. So the area of the curve would be the displacement. Now, you can be given something like that. So all you got to do is find the areas and add them all up. A different way of looking at area in the curve is if we have a negative region. So I'll do something like this. All right. So what I'm going to do is I'm going to color in the areas on the curve. Remember, the strategy is always to go from the line, aka the curve, to the horizontal axis. So here's my line, and here is my horizontal axis. So that right there, okay, if this is a velocity time graph, this is my first displacement. So here we have a negative displacement. After that, we have this region here. And this is all my positive displacement. So here we have a positive displacement. Now, sometimes they'll give you a jump like this, okay, where this vertical line is just like a dotted line, just to show you that there is a jump. And there, remember, we go from the line to the horizontal axis. Okay, so this entire square rectangle region, that'll be my negative displacement. All right, so that's one way for area under the curve. And so the thing that you should take away from this is that the area under the curve for a velocity time graph is equal to your displacement. All right. Now, the other thing is the area under the curve for a acceleration versus time graph is your change in velocity. All right, so commit those to memory. Now, if you have a hard time with memorizing, like I do, you might use my strategy. Okay, base times height, multiply your axes, so acceleration times time, and that should give you your delta v. And we know that because acceleration is delta v over delta t, right? So if we do a times t, we get delta v. So this is all linked together. All right, that was a review. If you made it this far, good for you. If you learned nothing new, that means you're ready. If you did learn something new, thanks for watching. I'll see you next time. Bye-bye.